Okay. Sure.
Alright, so I put up the final homework. And if school mind's there, I can see you. I see you can...
Yes, good morning.
Alright, good. Good morning. Alright, so the final homework, I'll just mention a little bit before we start. But the final homework is basically the first homework to deal with you doing something to do with renormalization and regularization. Remember, this is this related word, which has to do with basically the technical details of how you isolate the divergent part of some integral. And you'll get to know how to do that using this thing called dimensional regularization. And you'll apply it to the divergence in quantum electrodynamics and QED that's called vacuum polarization, which is the main topic of today. Oops, don't want that on. So, and this will basically just be, it is a rather big computation, but it's in Peskin. So the homework is basically filling in the steps that Peskin leaves out. So it's a big calculation that's due with the final day of class, but all the main, the broad brushstrokes basically of the calculation are there in Peskin, and it's up to you to fill in the details. So that's the final homework. And today we'll go through a related calculation on vacuum polarization. And we'll talk about, in addition to doing, fairly explicitly the calculation in the related theory, we'll talk about the quantum electrodynamic result. And also how it relates to something called a renormalization group. So that's sort of a souped up way of dealing with renormalization. So, right, one important thing, this is sort of a funny name, but before we even do the calculation, I'll explain what the name comes from and physically how to think about what's going on. But basically, you can think of it as a loop calculation that modifies the photon propagator. And that's important because, for one, the photon propagator basically is what tells us that you get Coulomb's law. So if you remember that, it's the momentum dependence of the propagator, the fact that it was from a massless particle, that led to this 1 over r behavior, right? If we had a massive particle doing the exchange, we would have had something more Yukawa-like for the potential, right? So that's the first important thing. If we're saying, the first important thing is just recall that our so-called derivation of Coulomb's law certainly relied on the fact that my photon propagator, which I write with a mu and a nu on them, that this for the photon was minus I over p squared g mu nu. Actually, I didn't do this explicit calculation, I don't think, for QED, but we did it for lots of related theories. The g mu nu is irrelevant, basically. It's going to just the same thing that we saw when we had, scalar exchange. We looked at our, in that scalar Yukawa theory, we looked at the exchange of a massive or massless scalar, and we found that that was going to give us, that's really the information that tells us what the potential is. So this is basically how we would get out that we get Coulomb's law from ordinary electromagnetism, is because of that propagator. But certainly, this is not the whole story, right? Because we're fancy now, we know that quantum electrodynamics also has couplings to charged fermions. So there's an infinite number of corrections to this. the simplest one, so if I include one loop correction, for example, the photon could come along and then, for just a moment, turn into an electron-positron pair, or a quark pair, or whatever, some charged particles, and go back to a photon, right? So this is all that we're going to calculate. But the other important thing, right, is that, if I had a plus m squared here, certainly I'm modifying the momentum dependence, right? And that would show up in the potential. I'm certainly modifying momentum dependence too here by including some, I have now fermion propagators inside the loop, right? I have extra momentum dependence. So that's certainly going to modify the potential. So we know basically from quantum field theory, Coulomb is not complete, right? It's not the whole story, and one way of calculating, the way of seeing what the first order correction is from this diagram. And unfortunately, it's not an easy diagram. That's your homework, is calculate that guy. We're going to do a related diagram. And the reason this shows up also only now when we're talking about renormalization is that it's infinite by, in the naive way of calculating things. So in the naive picture, right, so I have an electron charge and an electron charge, and a d4p. You should integrate over all possible momenta there. And since I have two fermion propagators there, and each one goes 1 over p, this goes like over p squared, which this is a d4p. So that's certainly going to go to infinity if I let it. So that's the whole point of this stuff about regulators. We need to have a way to soak up the infinity, to isolate it basically in one term, controlled by one parameter. That could be your momentum cutoff, or it could be, I'm not doing the integral over 4 dimensions anymore. I'm doing it over d, because it's not always divergent. If I let d be something else, I can soak up the infinity in the dimensionality too. So that's the treatment that you'll do in the homework. And Peskin actually does, I think, a pretty good job of introducing it. It's a little less scary than it sounds. So, again, what this is sort of telling us is like the result that we did in class last time, which is basically that we need to renormalize the charge. What we need to say is, what do I mean by the charge? This thing in my Lagrangian, that's not actually an observable thing. I have to define what I mean by charge basically by some observable. I have to say, do some scattering at some momentum scale, and the coefficient that you get in front, that's what I mean by charge. And the physical consequence of that is that I tie it to a particular energy scale, and then all that this loop is telling me is how that process is going to change with a different momentum scale, right? If you go and do the same computation at some other energy, you'll get a different result, but it will be calculable and predictive without any infinities. So that's the trick of renormalization. So what we need to do is renormalize the charge. So is it clear too why this is the same thing as having a modified potential? So that's basically the same statement.
Sorry, why do you ask? Is it the same
So
thing?
is it clear that by what I mean by saying that I'm going to renormalize the charge, that's equivalent to saying that Coulomb is no longer the whole story?
Yeah.
Is that basically clear? Yeah. So we need to renormalize the charge, and so conceptually, this comes from viewing the vacuum as not just a static place. This comes from viewing the vacuum as a dielectric medium, basically. So imagine I have my bare charge, not something that's ever actually observable, but imagine I have I turn off quantum vacuum effects basically. So I have my raw electric charge, and what can happen, or what does happen in reality, is that there are really always E plus E minus pairs being formed in the vacuum, right? And moreover, they're in the vicinity of this field, so they're going to be polarized, right? So I always have some plus minus combo, but the plus side is always going to want to face towards the electron, right? Because I have this all over. And this partially screens the charge. Right? So if I wanted to, like always, you could do your test sphere stuff. Draw a little test sphere there to compute my effective electric charge. And I'll find that, this bare charge is partially screened by the vacuum itself. So I have some, this guy I'm calling my dipole. So this is some E plus E minus dipole with a characteristic length scale of the electron mass, 1 over the electron mass. So you need to go to small distances to see this effect, or equivalently very large energies, but it's certainly going to be there. So this is sort of a really schematic picture that you can think of vacuum fluctuations as screening the charge. If you have, really high energy, then effectively you can sort of penetrate further into this polarization cloud and see closer to the true charge. So you would see an effectively larger charge, right? So that's the picture. At larger energies, you should have a bigger charge, and that seems really to be the case. It's just a very, very small effect in quantum electrodynamics. The same effect is present, though, for quantum chromodynamics, and there it's basically the whole story about quantum chromodynamics. What makes it so different is that the effect is huge for quantum chromodynamics, and it also goes in the opposite direction. And there the force gets weaker with higher energy. Okay, are there any questions about that effect or any of this? So that's why it's called vacuum polarization. And for your homework, you're going to calculate that diagram, which is certainly a bit involved, but nothing you're not capable of. So what we'll do instead is the simplest theory you could study vacuum polarization in, which is scalar phi cubed. Not phi to the fourth, but phi cubed. It's almost the same. The diagram looks almost the same. So again, what I mean by this theory is it's theory with G phi cubed in it, and that G has units of mass, because our Lagrangian has to have units of mass to the fourth. And there the vacuum polarization diagram. So at order G squared looks basically the same, but we have all dashed lines for our one scalar that's in the theory. And because I have a cubic vertex, that's the fundamental vertex that appears there twice, right? So I have some incoming momentum, and I have to have momentum conserved everywhere, so that outgoing momentum is P. So if one of these momenta is K, then this has to be P minus K. All right, so we know how to calculate what this diagram is using our Feynman rules. I mean, we have studied this, I think, once or twice, but the only important thing that's different is, right, it's this vertex, which is going to come with a Feynman rule of minus IG every time it appears. So this ends up being, let's write down all the factors. So we have a minus IG squared, a d4k over 2 pi, so forth. We have to integrate over that loop momentum. And we just have two scalar propagators with different momenta. We'll have p minus k squared minus m squared plus I epsilon, and I k squared minus m squared plus I epsilon. All right, so the other important thing is, we're going to have p squared not necessarily equal to m squared. So this will often be the case too if I stick this into some scattering process, right? And look at the exchange of phi in phi scattering. So this is going to be someone who's virtual. So one important trick that I didn't talk about for dealing with these things, and that you'll encounter also in the homework, is something called Feynman parameters. So it's helpful, basically all of our helpful integration techniques deal with integrals that look like just having one of these factors. But here I have two. So it's helpful if I can basically combine denominators in a way so that I get something that looks like I have an overall square in the denominator. So maybe I'll start it here. So this comes up in almost all of the ways that you do all of the regulator techniques, whether it's in the momentum cutoff or dimensional regularization. So first trick is to introduce Feynman parameters. So there are more sophisticated versions of it, but the simplest form of it is if I have something that looks like 1 over AB, you can convince yourself that this is true, not especially time consuming, but I'm not going to do it right now. You can show that you introduce some new parameter x that I integrate over. If I do that, I get back 1 over AB. But we nicely will put it in this form, and then I can change the order of integration. I can do the dx first or the d4k first, but the important thing is that it's going to put all my momenta into some form where it's something plus something quantity squared. And I usually have a better idea of how to do those sorts of integrals. So this is a general statement of the Feynman parameters. That's what these A and B things are. So this is really some dummy variable that has to be integrated over from 0 to 1. So in our case, right, I could just read off what A and B are. So A is p minus k squared minus m squared plus I epsilon. And B is the other one, k squared minus m squared plus I epsilon. So the thing I need is that quantity in the denominator. So I'll need A plus B minus A times x. So let me just do it. Minus m squared plus I epsilon and plus B minus A. So the m squared will go away. I'll have just k squared minus p minus k squared, all times x, right? Yeah, the m squareds and also the I epsilons drop out. So this is the combination I am left with. Let me call this thing, this combination alpha. So it turns out it's nicer to rewrite this as, again, because yeah, let me just write it down first. Alpha is better written as, we can show that it's true, you can write it like this. That's k minus p, 1 minus x, quantity squared, plus p squared x, 1 minus x, minus m squared plus I epsilon. So that's not too bad to check explicitly. So should we do that explicitly to see that it's the case?
No.
So it's just algebra then. It's straightforward. So now we can rewrite loop diagram. So it's phi m loop. Some momentum dependence. I think when I wrote it down, I forgot a symmetry factor. So we should really have a 1/2 in front of the overall thing for identical particles. But it doesn't matter too much. So I have my d4k integral and now also my Feynman parameter integral. And now all over too much. Oh, I'm going to write it small. So it's k minus p, 1 minus x. Squared plus p squared x, 1 minus x. And the remainder of the minus m squared plus I epsilon. So the whole point is this is of the form, which is actually something we do know how to evaluate. It's what we did last time. So let me call that integral. It's schematically something that depends on some delta, where delta is just that guy in the denominator who comes along with the k squared, delta squared, plus I epsilon squared. Oh, sorry.
The whole thing's squared.
Yes, thanks. I forgot to write that final part. That's the whole point. Is that this is of that form. It looks rather messy. This is really just some k tilde though that I can transform things to. So it's just saying I want to do the integral of 1 over some k squared minus something, whole thing quantity squared. So it really is of that form. So I say we know how to do this, but we actually didn't complete that last time. We completed a related one where this is a cube. But if you know how to do the cube, you know how to do the squared also, because they're related by a derivative. So I could do, for example, what's di the delta. So that would be d4k pi 4 k squared minus delta plus I epsilon cubed, which last time we found was minus I 16 pi squared delta. So remember we did this last time when we did this rotate to, you do this Wick rotation stuff, so you can rewrite this as a Euclidean integral and you get some minus i's and stuff. But then having put everything just in ordinary Euclidean variables, then we can use the results of what are the surface area over a four-dimensional sphere. So that's where this prefactor came from. So right, important thing is that this integral, this cubic one, is actually perfectly well behaved. It's not divergent. But if I go back to the integral I'm actually interested in, I will get a divergence because I have this 1 over delta, right? So I'll have my, this will become minus I 16 pi squared log of delta over lambda squared. So this is the thing, the result that we're interested in, and also that we used last time in our first look at renormalization. For us, we have that this delta is m squared minus p squared x, 1 minus x. All right, so meaning, we now demarcate. So meaning, we can rewrite this whole thing, this m loop factor, as still a g squared, where now I have an I in front, and 32 pi squared. And now, right, now we can just insert our result for what the d4k integral is, but we still have our integration over the Feynman variables, which will now be our effective delta, which is m squared p squared x 1 minus x all over this lambda squared, which is the thing, our regulator, the thing soaking up the infinity. All right, so there's no approximations in getting this for the exact one loop result. So it's easier to say we'll work with and state and also study the explicit n equals 0 result. Which, right, so, which involves, of course, doing that integral minus p squared x, 1 minus x over lambda squared. So that is a slightly tricky integral still. You can do it. Does anyone have a good idea, by the way, how you would do it? It's a bit more troublesome with the m squared there, but setting that part to 0. Anyone have a good idea of how you go about doing that?
Okay. Ln A, ln B is ln A plus ln B.
Oh, just doing some log manipulations?
Just to start.
It's possible that may help. I don't know if it does. I mean, does anyone remember, by the way, how, we usually, the way you often will encounter log in an integral is that it appears as a result of an integral, like you do 1 over x or something. But Does anyone remember how you would do something like, what's the integral just of log x?
Log it.
So that comes up less often,
Yeah.
and it's a funny result.
X plus
Yeah. But where does that come from? How do we?
Trig thing? Or
From what?
is it a trig thing? Just
Again, it might be. It might be a way to do it with trig, but so one way, if you ever forget how to get what the log of x is to use integration by parts. So we can use integration by parts here too. So we're really interested in something, say, of the form log of ax1 minus x, something like that. So we can use integration by parts. Right? V du is u v minus u dv. And in our case, what we want, this is why it's a little funny, I guess. So we want to take v, the original function of interest, as just the whole thing, basically. Which means, and also what does that mean for du? It's just dx. So dv, what's nice about that, of course, right, is we know how to do what dv is. I don't know how to do anything with log except take their derivatives, right? So that's why you change the, you don't know the integral, we'll make it into a derivative problem then by using integration by parts. So that's the helpful way of thinking about integration by parts, is you're flipping a derivative onto someone else, right? Turning it all into derivatives, basically. So dv then is, well, I do 1 over, when I take the derivative of the outside function, I get just 1 over the integrand, so ax 1 minus x. And then I have to do the derivative of the inside, which is just going to be a, so I can think of this as x minus x squared. So the x just becomes 1, the x squared becomes 2x. And my u becomes x. So now, right, I won't do all this stuff, but u dv is going to be something simple now. Something that's just a normal polynomial, basically. So there'll be one, maybe I'll show you the rest, just to be clear. So, right, we'd be writing our log ax 1 minus x. So I want uv, so x log ax 1 minus x minus the new part. So the a's go away, and when I multiply u times v, the bottom x will go away. So this will be minus 1 minus 2x over 1 minus x, right? Or did I forget something? Right. So anyway, this you have to further manipulate at the substitution. At the end of the day, the whole thing is this part, of course, stays 1 minus x plus 2x minus log of 1 minus x. Or even more simply, this is the indefinite integral. The thing we really care about is the definite integral from 0 to 1. That's actually anomalously simple to write down. When you plug in those explicit values, it ends up being just log of a minus 2. So okay, that's the only thing we wanted to know, basically. It was left to do the calculation. So we can just write down what our final amplitude is, or almost final. We still have this 32 pi squared. Both sides have an I, so I get rid of the I. 2 minus log of, this ends up being minus p squared over lambda squared. So the 2 is not physical. I can choose a different lambda, basically, to effectively get rid of that 2. So the factor of 2 isn't physical, since you can rescale, lambda can be rescaled. And moreover, right, we're interested in this process where those 5s are really off-shell states, right? They're virtual particles being exchanged in some scattering process, in which case this thing is going to be some space-like momentum. It's going to be something that's just exchanged, instantaneously, basically, in some scattering. So, and p squared is space-like. So let me just write it as not space-like, space-like. So we'll write this as our final result we'll talk about in terms of the actual momentum transfer. 32. Log of q squared over lambda squared, where this q squared is just minus p squared. So this is our first order result of the correction to the scalar propagator in this phi cubed theory. So now let's go back to this whole yada yada about renormalization and how do I get rid of the infinity, right? So far, I've completed the steps of regulating the infinity. Now I understand what's controlling the infinity is this lambda thing. If I naively let that float off to infinity, everything explodes and I can't predict anything. But that infinity appears in exactly 2 places, and I can use those 2 infinities to kill each other and give me something that's totally finite and have predictive results. And the way I do that basically is by defining what I mean by charge. So you soak up the infinity in that definition. So what we just did was again using this momentum cutoff regulator, and so basically the same set of steps you'll redo following Peskin. The techniques will be a little bit different because you'll use dimensional regularization, but otherwise everything's very similar. And the first step will be also using those finite parameters to put things in that sort of form so that it looks like one big thing, quantity squared in the denominator. All right, so what did we do? So we've effectively found a correction to the propagator. Because, for example, we write that the first order correction, right? What I was doing before is sort of the the zeroth order result, say for scattering. Say I'm interested in scattering in this theory, right? The zeroth order thing, just at tree level, where the momentum that's transferred is p. That's easy to compute. It's I g squared because I have 2 couplings that enter in the scattering event, and they're suppressed by 1 value of p squared. And again, so also the reason now I'm going to start talking about a scattering process, something more physical than just a propagator, is I want to soak up the infinity here. So that's what the technique of renormalization is it's going to say, we're going to define what I mean by a charge explicitly in terms of an observable. So there's no better observable than you go and do some scattering at whatever energy and go look at what the amplitude is. So the zeroth order process right? It was just going to be these two couplings divided by the propagator. We found how to do now the next order correction, which is these guys decide to have some fun in between the two scattering particles, and they turn into some particle-antiparticle pair momentarily. So I still have the same momentum flowing through there, and everything's the same, but now we'll have, now basically I'll have this, p squared on either side multiplied by the loop process I just calculated, right? My M loop. Oh, sorry, this should really be, oh, I guess that's right, yeah, over p squared. So I can write that as IG squared, p to the fourth, and minus g squared over 32 pi squared log squared over lambda squared. So the whole thing, at whatever momentum transfer, is g squared over q squared, 1 minus 1 over 32 pi squared, g squared over q squared, log of q squared over lambda squared. I still don't know how to make any predictions because I'm confused by the presence of lambda, which is a parameter I don't know the value of, and I easily want to set to infinity, so haven't done anything yet. But now we have to define couplings. So this is called the renormalization condition. It's the same set of steps we did last time, but you have to decide once and for all what you're going to call your renormalized charge, or what scale are you going to define things. Right, to make this as most directly similar with quantum electrodynamics, we should turn our coupling, which is dimension full, into something that's dimensionless. So basically, to make things less confusing, maybe just because we're biased by thinking about marginal theories always, which have dimensionless couplings, we'll define the a tilde coupling, which is just the same thing as our normal coupling squared, but now divided by the only mass scale. In the problem, we have a massless theory, right, which is the momentum scale, the momentum transfer that's going on in the collision. All right, so, and in other words, very straightforwardly, we can just rewrite this as just a coupling squared with tilde coupling. This is just rewriting things. But now we can define coupling. We define our renormalized charge or coupling which is, I define it to be the amplitude for scattering at some fixed momentum scale. Right? So this is the big difference between that G and this G. Right? This is just something floating around in your Lagrangian, and that's all that it is. It's some number in your Lagrangian. This, however, is something physical, right? This is saying it's a number I directly relate to a scattering amplitude at a defined momentum. So this is also called renormalization condition. And you need one of these for each parameter in your theory, basically. All of the parameters in the theory get renormalized in quantum field theory. And it's always the case that you define the renormalized coupling or parameter, whatever it is in your theory, in terms of some observer. And that's the trick that lets you get rid of the infinity. So one condition per parameter. You don't want to have two, or you'll get inconsistencies. All right, so this, by the way, also, of course, right, this defines the connection between what's the renormalized coupling and what's the bare coupling, or the Lagrangian coupling. So, right, we could just think of the renormalized coupling as a power series in G tilde. Right? I mean, that's clear what it is. It's just that GR squared is this. But I can also just invert that. If I invert the relationship, I can get that what is the bare coupling in terms of the renormalized coupling. That's actually even more helpful. Because now I can just insert this back into my amplitudes and I get rid of the lambda squareds because I'll have some difference of logs. So those can group together, and now I'll have just log of q squared over q naught squared. And I'll have everything in terms of the renormalized coupling. So now I'll insert my g as a function of g renormalized into my scattering amplitude to eliminate lambda. So this is, again, exactly the same steps we did last time with a different theory and slightly different prefactors and everything, but so it's, by definition, it's g tilde squared at q naught, and anywhere away from that, you can compute the correction from that logarithm. So this is up to order g tilde to the 6th. Oh, sorry, this is the 4th there. So that's the important thing, is that this has soaked up the infinities. It'll be, by the way, a little more, it'll be different for sure when you do the dimensional regularization. So here it's a little easier to think of there being new physics at some actual physical cutoff scale, some new high energy, and that being the thing that, is the source of any potential divergence in your theory. But instead what you'll have is some amplitude now that's a function of the dimensionality, right? Because that's the new variable, the new freedom you give yourself when you do dimensional regularization. And typically what you do is expand the dimensionality around our dimensionality, around 4. And so you'll have some d, the dimensionality is equal to 4 minus epsilon or something, where epsilon is, always some small number, so you're always really close to it. And you'll have expressions that instead of log of some cutoff scale, they'll be just 1 over epsilon. And you're taking the limit that epsilon goes to 0 at the end of the day, and that's the source of your divergence. But again, the same steps will work out. You just define things at some cutoff scale, and you'll be able to get rid of that epsilon in any physical process. So that's the trick. All right, so let's talk about what happens in quantum electrodynamics. I'm going to not do the result, but I'll just quote the result and talk about it a little bit. And also talk about a subtlety that will come up maybe in dimensional regularization. But things are similar in quantum electrodynamics. So there, like we wrote before, I have some process like this, where my photon can come in and spontaneously turn into E plus E minus pair and reconstitute as a photon. So it turns out we can argue on pretty general grounds it has to have something that looks like, so the factors of I and so on are convention, but it has to have something of the form p squared g mu nu plus p nu p nu. And I have two couplings, so I know it's going to be a e squared. And the rest is the thing really that you should focus on in the calculation that Peskin leads you through, which is this thing which we just call the vacuum polarization in quantum electrodynamics, this pi 2, which is just a function of momentum. Right, that's the other, of course, when you first write down, just from Feynman rules, what this thing is, that's the first big difference, is that now, right, I have indices to worry about that I don't have in the scalar case, but all those indices are soaked up by these factors. So everything can be written just in terms of the scalar function. And the explicit form that you'll find is that this is 1 over 2 pi squared, 0 to 1, dx, x1 minus x, the same Feynman parameter, 2 over epsilon, and log of some new scale, which I'll talk about, m squared minus p squared, x1 minus x. So again, it's not that different from the sort of thing we find in for vacuum polarization in the phi cubed theory. So, but I have to comment on what these things are, by the way. So this thing, this is that divergence, basically. That in dimensional regularization, we're going to treat D as a free parameter, and ultimately, since we're interested in D equals 4, you'll take the limit that this, infinitesimally as you approach D equals 4. So you allow for just some small deviation, and that leads to the leading divergence, which is this 1 over epsilon piece. The other sort of funny thing in that expression is this thing, this mu, right? So the whole point was that we didn't need any, no. Here we have some new cutoff scale, some new energy scale, but that's explicitly because of our regulator. Here, all the soaking up the divergence is supposed to come from our dimensional trick, which has nothing, has no units associated with it. But we have to be careful because when we allow ourselves the freedom of going into different dimensions, then all the parameters in the Lagrangian also have different units, right? So, so what does mu delta squared come from? So this comes from the fact that, again, we always have that the action is something unitless in all dimensions. So that means, right, the action is the space-time integral over the Lagrangian density. So that means that the mass units of the Lagrangian are d, in d dimensions. And what does our Lagrangian have? It contains things like f mu nu squared, for example. That's the part that's the kinetic term for the photon. And this is something like derivative of A squared, right? So this always has units of, the derivative is always just one mass unit. So it's 1 over a space unit. So what does that mean? That means, right, I'll have, I always want this to be units of B. So I'll have D over 2 and minus 1 for the space derivative, that's going to be the units in general of the photon, or of the vector potential. So right, and if I take d equals 4, then I'll have 2 minus 1 or 1. So that gets us back to the thing we always knew was the case. What about psi? What are the mass units for the electron field, say? Well, we could look at the kinetic term that just comes from the Dirac equation in the Lagrangian, right? So we have something like that. So again, we'll have one space unit, and we'll have two fields for the, so this also has to have units of d overall. So what does that mean? I have to have d minus 1, and this will be 2 times the mass unit. So I'll have to divide by 2 at the end. So the mass units of psi are d minus 1 over 2. So again, that'll be 3 halves in 4 dimensions. And the funny thing, this is why we have this new scale, is if I look at the interaction in QED comes from E, the coupling, times psi bar, gamma mu, psi A. Right? That's my coupling between a fermion and a photon in d dimensions. That means, unfortunately, like that we should have guessed, is that E, the coupling, is not dimensionless in general. Right? The units of E, you can check, are 2 minus d over 2. So that's what this mu thing comes from. It's just basically saying I want the thing that I'm going to write as little e. I'm going to always want that little e to be dimensionless just by convention so that it's easy to understand how I recover the normal limit. And so to do that, I have to introduce some new mass scale there to soak up the units. So then it's conventional to define. Your coupling has mu to the 4 minus d over 2 times e, where this is always unitless. And this is some new mass. So that's what that mu is sitting over there in the result that you'll try to understand. And it should be pretty understandable. I mean, Peskin really does do a good job, I think, of walking me through the main steps. So right, just like we did in our bi-cubed theory, this basically corrects the photon propagate. So vacuum polarization. Corrects the photon propagator. So we can write down, we'll introduce some notation for the full photon propagator, call it G. So we'll write it as being the tree level result plus 1 loop correction, where we always have some T going through there. So this is the photon propagator, or corrected propagator. Also sometimes called the dressed propagator. So it's not, everything that doesn't have loops are usually referred to as bare results, like the bare coupling. So this is also the key to understanding why we have a modified potential. We don't just have Coulomb anymore. But I could rewrite, remember what that thing is, it's minus I g mu nu over p squared. then I'll have two propagators plus my loop result. So I have a minus I p squared I pi 2. So this whole thing, I should say, whole thing is called pi nu. So 2. 2 just because it's just two fields that are external. And maybe minus I p squared. I also have these mu terms, but those don't contribute to modification of the propagator. But in terms of thinking about what's relevant for modifying the propagator, these are actually not going to be relevant for when you insert this into some scattering diagram. You'll see that those vanish because of the spinner conditions. So I can think of this as basically leading to this sort of correction. Let me regroup things so that I pull out the conventional factor and have a p squared overall. Does it mean I can think of this as being 1 minus e squared pi 2 squared times g mu nu plus those same p nu terms. So this is really contains all the new momentum dependence for Coulomb's law. This is basically, this will give me a, it is essentially the Fourier transform of the potential. And also gives us an idea of how we might define the renormalization condition for QED. So this also directly contains a Fourier transform of the Coulomb law, not really Coulomb anymore. So that Fourier transform is just this e squared and 1 minus e squared pi 2 e squared. So a natural choice might be natural choice for the renormalization condition. Might be, I take some characteristic length scale, call it R naught, and I define my renormalized charge to be the normal Coulomb's law, right? You could also imagine that as the natural choice if you want to just, sort of be an ostrich and bury your head in the sand about all these annoying new corrections. You could just say, look, I like this energy scale or distance scale R naught, and I'll just define my charge to be whatever it needs to be to have the normal result hold. That's fine, but it's only going to work at that one scale, right? So it's really, this is the equivalent of what we did before when we were defining our renormalized charge or renormalized coupling in the phi cubed theory. And the upshot being that you can rewrite, you could go through basically exactly the same steps that we did before, but now the thing we need to worry about, the observable we're soaking up our definition in is in the potential. We're assuming that's something you can get directly from data, which now I could, in the ordinary, our pre-renormalization condition way of writing it would be e squared minus e to the 4th by 2. But now I can rewrite, this also gives me a dictionary for how to relate ER squared to the Lagrangian level coupling. So I can rewrite this potential now just all in terms of renormalized charge and the difference of pi 2s. Minus pi 2 p naught squared. Where p naught and r naught go together. So from this, it's not super illuminating to write down the explicit form for what the potential takes, except in one limit. So let me write that down because I think it's interesting. This was discovered, I think, in the late 40s by someone I've never heard of, and also don't know how to pronounce. The Euling potential or something. So in the R much bigger than 1 over the electron mass limit, this is called the Euling potential. And it looks like minus alpha over R, of course, is the main thing we've heard of, Coulomb. And the new part is alpha over 4 square root of pi, some prefactors that are dimensionless, and something that looks very Yukawa-like. So something probably we should have been able to guess, at least the exponential, the main effect we could have been able to guess maybe from our little picture of thinking of the vacuum as being built out of dipoles of a size 1 over 2m because of the electron-positron mass scale. But this is something that can actually be investigated. It's very hard to see, though, in scattering experiments because the charge is so small. So, right, another alternative too, and that's actually more useful in practice, especially in particle physics, is not to define everything in terms of some potential, which might have been useful to do in Coulomb's time, but instead to define things in terms of scattering amplitudes. So just like we did before too, or yeah, and alternatively, some effective charge that grows with momenta. It's a renormalized charge, 1 plus ER squared over 12 pi squared log of q squared over m squared. Where this thing would sit right in front of the momentum-dependent potential. So it would be the Fourier transform of the potential, which I would define as being effective charge squared over the momentum squared. Just to have it have the same form of what the tree level result looks like. So right, it depends on how you want to think about things. You want to think about things as having some modification to Coulomb's law, or in sort of more modern parlance, you want to think of it as there being some running coupling, a coupling that just changes with energy scale. It's not a coupling constant anymore, but something that changes. It's very hard to see for quantum electrodynamics, but has certainly been verified. It also leads to an important point that quantum electrodynamics predicts that it should cease being a reasonable theory at some point. So it's hard to observe since alpha is small, but we can rewrite, if I want, I can rewrite this effective coupling squared just in terms of my alpha effective as a function of energy. So to put in numbers, right, I should get at small momentum transfer, I get back the ordinary thing that everyone knows, the 1 over 137. And now everything is controlled by, what that low energy value of the coupling is. And so it ends up being 0.00077 log q squared over electron mass squared. So at relatively low q squared, or any even reasonable q squared, this is a pretty small correction, which is why it's really hard to see. But there's another important point is that, right, whenever throughout all of perturbation theory, the power of Feynman diagrams relies on this term being smaller than this term, right? So it tells you explicitly when perturbation theory will fail. So it also signals the demise of perturbation theory. When this, in order to have the first and second terms be comparable, this has to be 10 to the 286 eV. Some enormous energy scale for quantum electrodynamics. If this prefactor, though, was a bit different, right? Or in other words, if the low energy value wasn't 137, but something a bit bigger, this might be something observable. But anyway, this is called the Landau pole. All many theories have such a thing, where perturbation theory ceases working. And it's not anything that's observable in the real world, right? This is far beyond the Planck scale, far beyond any number you usually encounter in particle physics. So the one last sort of interesting thing I want to mention that starts to connect with what's called the renormalization group is the fact that we can, before I wrote down our propagator, I just included those first two terms. But we know how to include an infinite number of them actually right away. So my way of thinking of the full photon propagator is, or at least for a class of contributions, of mini loop contributions, right? We just wrote down the first one. It's clear at least how I could write down something explicit that incorporates all diagrams that look like this. I just keep on inserting the one loop in the middle over and over again, an infinite number of times. That's basically a geometric series. So I could write down the contributions to the potential, again, just being of a very similar form to this. So the first order result is the ordinary Coulomb. Then I have my ER squared, 12 pi squared log. And the same thing squared, this same factor squared. Right? There's a name for something like that. If you just have 1 plus x squared plus, it's a geometric series, right? So we know how to write that down explicitly. So it's just 1 over ER squared q squared, 1 over 1 minus that thing, right? So this I can think of as now this is a geometric series. So I can think of this as being my, plus this factor, as being my new effective charge. That incorporates the effects of an infinite number of Feynman diagrams. So another, the final important thing I just want to mention, which is the language people have for talking about general renormalization of couplings is to notice that, right, everything, you know, we did this before too when we introduced the renormalization procedure. You always introduce some arbitrary scale where you have to actually do some measure, right? But at the end of the day, the theory doesn't really care about that. So we could reformulate everything without any q squared in it somehow. And just look at general variation of the parameter. So there's nothing special about some explicit q squared. Can instead study the renormalization of parameters through some differential equations, basically. So, for example, which are variations of the coupling. So, for example, in our theory, I could look at how does the coupling change with the energy scale. So I introduce some mu, some energy scale. And the right-hand side is something just from the theory, something I get just from the Lagrange. It's not, there's going to be no reference to the explicit energy scale there. And for QED, at one loop at least, this is the effective charge cubed over 12 pi squared. This thing is also called the beta function for QED. So this result is called the one loop beta function of quantum electrodynamics. And the sign is very, very important. So the sign is really the thing that indicates that this coupling grows with energy. And what was maybe the only time ever that the Nobel Prize was awarded for getting a sign correct, quantum chromodynamics has the opposite sign. And it wasn't until the 70s that people knew how to calculate that and deal with all the infinities. And you can calculate actually what the result is in quantum chromodynamics for arbitrary number of quark flavors and arbitrary number of colors. And in our particular world that has 6 quark flavors and 3 colors, this ends up being a minus sign with very important effects. So it'll also mean you can go and try to study the Landau pole for quantum chromodynamics, and it's instead something very observable. It's around 200 MeV, which is where hadrons exist. That's why they exist there. And so that effect is very non-trivial in quantum chromodynamics, right? You get out a new energy scale from the dynamics of the coupling itself. There's no masses inside the Lagrangian of quantum chromodynamics that point you to a couple hundred MeV, but it comes out from the evolution of the coupling. So it's basically the particles in the loop in quantum chromodynamics that create the mass scale that gives rise to all the masses of baryons and everything. So, but that's of course a significantly more involved calculation when you have quarks and colors and things going on inside the loop. And an important thing is that gluons themselves will contribute. You can have gluons as bubbles as well. And those actually are the crucial fact that lead it to be a minus sign. But so this concludes basically our story of renormalization. You'll get familiar with some of the technical details. Hopefully you'll still have hair left over by the end of it because it's a little bit of a involved calculation, but Peskin will help a lot. And then so for the last couple lectures I'll focus on spontaneous symmetry breaking and the Higgs mechanism. So I think that's the other big, important conceptual topic for the real world. Cool. Any questions about anything? Covered a lot of things today, but to give you a flavor of renormalization and how it connects with other forces and all that. All right, yeah, by the way, so that last homework too is also due the last day of class, so December 3rd. So if you don't want to work on it over Thanksgiving, that just means you have still one more week to do it. So.
Give me a ride to Burger King.
Yeah. All right, but have a good Thanksgiving. See you guys in a week.
Thank you. Have a good holiday.
Thanks, you too.
जाडोमा त पेट झन् लाग्छ रियाक्सन त
Hey, how's it going? Sorry I didn't get back to you. No, it's been very busy. Right. Yeah, probably we can. We meet at like 9.
Yeah, anytime.
Yeah.
I have no class.
Yeah, let's do 9. But also send me an email.
Yeah.
Is that good?
Yeah.
Okay. Yeah, sorry about that.
Yeah, that's okay. Thanks.
Yeah. How's the class? Is the class okay?
Yeah.
Yeah. Good.
I just need some solutions.
Sure.
Yeah.
And you're applying too, right?
Yeah.
Yeah. How was that?
Yeah, that's the thing that I